Hey there, how are you doing? My name is Luigi Petruno, and I wanted to spend some time today talking about what happens after you build your first set of machine learning models. This talk is directed primarily towards data scientists and machine learning engineers who spend their time building out features, trying different model architectures in order to build the most predictive type of model possible, who may not know what to do once that model is built. For example, suppose you're trying to predict some target and you've spent some time building out models and you've built your first pass model and you're pretty satisfied with the performance and you're wondering, what do I do next? How do I get this model into production? And how do I get this model delivering value either for my company that I'm working for or for an organization that I'm working with? So before I dive directly into the topics I want to talk about, let me just introduce myself and say a little bit about who I am. I'm the founder of mlinproduction.com, which is a blog and newsletter dedicated to teaching people how to build production machine learning systems. I started that blog about a year and a half ago after I noticed that it was really difficult to find any content whatsoever about building real machine learning systems in industry. Most of the content that I found was either about learning algorithms or was really targeted towards beginners. And I wanted to give professionals, people who are working in the field, a place to be easily able to find content related to challenges that they were facing in their everyday job. I'm also the director of data science at a company called 2U, and there I lead out a team of data scientists and machine learning engineers building predictive models to optimize the business and also building out predictive infrastructure to support our model building process. Before that, I've held a number of roles as an individual contributing data scientist, an ML engineer, and a data engineer. So I really consider myself a full stack machine learning person because I've seen and worked on things all the way from building out ETLs and really thinking about data quality issues to building research infrastructure, doing things like visualizing model performance on high dimensional, high throughput time series data and building models on that, also to building out predictive models on all sorts of data related to business problems. And I think one of the more important things I like to say about myself is that I'm a product-driven data scientist, right? So my primary concern is how to solve the problem at hand. And if solving the problem at hand means using a linear regression, I'm more than fine doing that. In fact, I'd prefer that because it's much simpler. So I'm not overly obsessed with methodology, overly obsessed with what particular tool or algorithm do I use in the situation. I care more about actually solving the problem and delivering value that way. So if you want to reach out to me, feel free to shoot me a question on Twitter, and you can find me at mlinproduction. So to start my talk, I want to use a motivating example to discuss that we can use for the rest of our conversation. So there's a huge difference between these two photos on the screen here. On the left-hand side of the screen, we have Google Smart Compose. And Google Smart Compose is a feature that came out about a year ago, and it allows you to automatically complete your sentences and phrases while you're writing an email. Right? And this is a pretty magical experience if you've used Google Smart Compose before, either on your desktop or on your laptop or on your mobile device. When you start writing, Google will recommend you the next few words to finish out your sentence. And one of the really impressive things about the feature is that the experience itself feels really intuitive and natural. So for example, Google doesn't automatically finish your sentence for you, right? It doesn't just inject the text into your email. It first displays that text in this really light gray font color, which when you see it tells you that the text isn't there, but it can be there, right? And in order to actually select that you want that text to be filled in, you have to, if you're on your laptop, hit tab, and if you're on your mobile device, you just swipe right. So the user interaction, the ability for you to actually tell Google, yes, I want to use the text that you're automatically suggesting, is very intuitive and makes your life very easy, right? So if you use this product, it feels really, really intuitive and magical. You don't have to do too much thinking, and utilizing their suggestions is really easy. Now, the ability to do that well, the ability to build in that user interaction and those design elements that I mentioned, have really nothing to do with machine learning, have nothing to do with feature engineering or building out models. They're much more to do with design and product development, right? So the image on the left here represents a product, right? And what goes into a product is much more than what goes into a machine learning model. Even though a machine learning model is part of the product, there are many other parts of the product that enable it to feel as intuitive and useful as it does. On the right-hand side of the screen, we have an image that represents the actual neural network architecture that underlies the model within Google Smart Compose. And the model on the right is what data scientists and machine learning engineers spend most of their time doing, right? They'll try out different neural network architectures, they'll try out different features, they'll run many experiments. Most of them will fail, but they'll keep iterating and doing error analysis until they wind up iterating towards a model that works quite well. So this is what data scientists and machine learning engineers focus on the most, but this is not where the value comes for the user, right? The value for the user comes when you package your model into an application or a feature or product that works as well as Google Smart Compose does. So I want you to keep this sort of dichotomy in your head, right? There's a product and then there's a model. And what delivers value for users is the product, not the model. Although the product couldn't be possible without the model, the product, could rely on a simpler model, for instance, or a different model, but the model itself really won't provide value to users. The users need to be able to interact with the model in order for value to be generated. So the process for actually building this product is very different than the process for just building the model. And when we want to think about, what happens next in the model building process, well, we really need to think about the entire design process of designing a machine learning product. Right, so this is an image from a blog post written by Fabien Girardin, and I've linked to the blog post in the bottom left-hand side of the slide here. And what this image shows us is that designing machine learning products is really an iterative process, right? And that iterative process starts with some question or some idea of something we want to build, right? Or some challenge. And once we have that question or idea, which is something that's motivated by a user need or a need of some sort, then we begin this iterative loop. And the first thing we do is generate some hypothesis. For instance, what do we think we can build in order to answer this question or solve this challenge or exploit this opportunity, right? So if we think of an example, for instance, let's stick with our Google Smart Compose example. The question might be, what feature could we build to make writing emails a more seamless process for users, right? Rather than having them write out their text, how can we make it easier? How can we, simplify the process of writing emails? That might be the question, right? Or an opportunity might be, hey, some of our data scientists have developed these really cool algorithms that allow us to predict the next few words of text. Since we have this functionality, what kind of product can we build, or what kind of features can we build in our existing products that allow us to exploit that new functionality that we have, since data scientists and the machine learning engineers have been developing these things on the side, right? So notice, one is a question that comes from the user side, right? How can I improve the user's life? And the other is an opportunity that comes more from the functionality side, the algorithm side. Hey, we have this algorithm. What can we do with this algorithm? What new feature or product can we build? All right, so they're two different things, but they both speak to the fact that the model itself won't deliver the value on its own, right? We need to use that model in some way. And once we have that hypothesis and we have some, we can design some data set and we can, research whether or not some solutions exist, we then enter the prototyping stage. And this is where most data scientists and machine learning engineers work, right? They try out different algorithms, they visualize their results, they evaluate whether or not the algorithm meets some minimum level of performance. And from there, they just iterate and iterate and iterate. And this is where most data scientists spend their time thinking about, but this is just a small part of the problem, right? And from there, we can now determine whether or not the model is performant enough. And if it's not, it may mean continuing to iterate on the model within the same sort of paradigm, within the same sort of hypothesis paradigm, or it may mean iterating on the hypothesis itself. Maybe the class of algorithms that we're trying out really aren't performant enough. Maybe we need more data, right? So this may mean, the loop could be around building more features, or it could be around building a new data set or trying to solve a new problem. And, if we evaluate the model and it does perform as well as we'd like, we then can deploy that model to production, but the sort of work doesn't end there. From there, we might want to continue collecting more data from users in order to improve the product further. We may redefine our problem if we find that even though our model met certain performance thresholds in terms of the ability to predict things, we may find that it's not delivering the user value that we originally anticipated, and we'll have to start from scratch. So this is the process of designing an entire product, right? And it involves not just machine learning engineers, but it involves asking business questions. It involves user research and user development. It involves design, because the interface that we provide to users for interacting with the model, that's a non-trivial question in order to come up with an interface that works well, right? The Google Smart Compose interface that we discussed earlier, it wasn't trivial in order to just come up with that interface. Many people had to work together to think through how best to showcase the predictions that the model was generating, how best to allow people to select that they wanted to use the suggestions. So these are all parts of the problem of coming up with machine learning powered products, and by no means are any of these simple things. They require people with different skill sets, and they require a lot of iteration. So let's focus on the actual machine learning part of it, right? Let's hold the design elements and the business questions aside for a second, and let's just focus on the actual model building part, because machine learning engineers and data scientists, that's what they focus on. So the process of actually building out the model is actually a sub-process of this entire product design process itself. So this figure is taken from a paper that was published by Microsoft a few years ago, and the name of the paper is Software Engineering for Machine Learning, a Case Study. And how the paper was developed was a team within Microsoft went out about surveying different teams at Microsoft and trying to learn how these different teams used machine learning, what their challenges were, what the common challenges were, what the sort of different challenges were between each team. And they performed those surveys and synthesized their results all into this really excellent paper that I highly recommend you reading if you want to learn more about how machine learning work gets done at a huge company like Microsoft that has a very advanced machine learning practice. So I highly recommend reading the paper. And one of the figures in this paper is this one here on the screen. And what this figure shows is the stages of a machine learning workflow that they were able to extract from across different teams at Microsoft. Right? So they ran their survey. They asked these different teams how they do their work. And this is the general pattern that they were able to extract from across these different teams who worked on all sorts of use cases, right? So this is the model building sub-process. And it starts with collecting out the model requirements, collecting data, cleaning that data, labeling that data, feature engineering, model training, model evaluation, model deployment, and model monitoring. So if you don't have much experience deploying machine learning solutions in industry, right? If most of your experience comes from actually training models, feature engineering, right? And this is even the case for people who are in academia who may build a lot of machine learning models, but the process really ends after they've built out a model. Or if you've participated in a number of Kaggle competitions, you really focus on the feature engineering and model training components, right? And many data scientists and machine learning engineers, that's what they focus on most, right? But that is a small part of one sub-process, which is just a sub-process in the larger process of building machine learning models. machine learning powered products, excuse me. So, if you spend your time in Jupyter Notebooks, most of the time what you're doing is feature engineering and model training, which are those two middle processes there. And the arrows in the figure are meant to represent that this process has feedback loops, right? So you may develop some features, you may train your models, but then you'll find that your models may not be performant enough. So you go back and engineer more features. Now, what I want to focus on for the rest of our conversation is actually the three last pieces of this sort of machine learning workflow. It's the model evaluation piece, the model deployment piece, and the model monitoring piece. And the reason why I want to focus on these things is because they are arguably the most important part of this workflow, of this sub-process, and yet the part that most people have the least experience with. And the reason they have the least experience with this is because you really need to be working for a company that's actually building out and deploying these sorts of products in order for you to have any experience, right? In terms of deploying your model, you can for sure, build a Flask API and deploy your model on your own. But if nobody's using it, you don't really have to solve the challenges of companies who are deploying models that are being heavily utilized. And in terms of model monitoring, well, same thing goes there, right? Even if you set up your API and you want to monitor your models, if nobody is using your models, well, there's nothing really to monitor. So what I'll focus on for the rest of our conversation are these three pieces. And again, I'll state, I argue that these are the three most important pieces of this entire sub-process. So let's start with model evaluation. So the important aspect of model evaluation is you really want to understand how costly an error is for your model. And what I mean by that is, let's think about a binary classification problem. All right, you build your binary classifier, and now your model can make certain types of error, right? You can have false positives and you can have false negatives. So it's incumbent on the person building the models to understand which type of error is more important, right? If a false negative doesn't really, hurt your user that much, but a false positive does, then you're going to want to make sure that your model is tuned accordingly, right? You won't want to commit false positives, but you might not mind committing false negatives as much. And that's just one example. And the best way to do this is to really put a dollar value on a model error. So when you put a dollar value on that, right, and estimating that is going to be a process that involves different people at a company, you'll be able to really evaluate like the cost of your model being deployed and not behaving as appropriately or as performantly as you'd like. So when you go about actually building a machine learning model in industry, I suggest that you do a couple of things up front. One is you really spend time thinking about your evaluation approach, turning that into a performance metric, and then defining some minimum threshold of predictive performance. And why this is important is because you'd like your evaluation approach to match how the model is going to be used when it's deployed as much as possible, right? So my team spend a lot of time thinking specifically about the evaluation approach each time we have a new project. And if it's possible, you want to assign a dollar value to the types of errors that can occur, and you want to understand the ways that your algorithm can fail, right? And typically, the way that most data scientists and ML engineers try to understand this is by defining some sort of overall performance measure like accuracy or F1 score or area under the curve or RMSE, and then building their models and just computing this score across some held out test set. And I argue that this is a good first approach, but this is not a reliable way of really understanding how well your model performs, right? And the reason that this is not a good way of evaluating your models, at least not the, it's a good first pass, but it shouldn't be the only thing you do, is because you really have no understanding of how your model performs on individual cases, right? And if you have users using your model and they have a negative experience with your model, well, no one's going to care if you achieved 95% accuracy across a test set, right? The business is going to care that somebody had a negative user experience, and that's going to look very bad on your team and perhaps you individually as a data scientist. And a good example here is when Google released an image classification system, and that system started classifying black people automatically in images as gorillas, right? So we can imagine the amount of pain this caused for people. And this error wasn't caused by a small no-name startup, right? This error was caused by arguably one of the largest companies in arguably the largest company in machine learning today. So if a company with resources as wide and expansive as Google can have this misstep happen, then imagine what can happen for a company or team that has far fewer resources. And most teams have far fewer resources than the Google teams, right? So what I want to point out here is that putting out a model, deploying a model that performs badly, even just on subpopulations, is worse than putting out no model at all. Because at least when you don't put out a model, there's no chance for these random errors that you don't understand. Whereas if you do deploy a model that you don't understand how it performs in individual cases, there's a chance that some really negative experience happens, right? Just like this experience I brought up for Google's image classification system. And I think this image on the right really captures how some people think about building machine learning models. And it's an XKCD comic. And there's two people in the image, and one of them says, so this is your ML system. And the guy on the top, who's supposed to be a data scientist or ML engineer, says, yep, this is what we do. We just throw a bunch of data into it. We run some linear algebra, and we get some outputs. And when the person asks, well, what happens if the outputs are wrong? The guy on top says, well, we just stir the pile around until it starts looking right. I mean, this is obviously a joke, but it really captures how some data scientists think about their problems. And they don't do this, malevolently, but they just don't think through it enough, right? So crafting your training and test sets and then just running, cross-validation until you achieve, the best performing model in terms of some score is not enough, because you don't understand how that model performs on subpopulations of your data, on subslices. And I read a paper called Ad Click Prediction, A View from the Trenches, and this was a paper by Google. And they had this really nice figure in here, in this paper, and talked specifically about this problem. And the way they talked about this problem was when they were building out their system for understanding if users would click on particular ads, what they wanted to do was evaluate the types of queries that users input into the Google search bar and determine how well their click-through rate prediction models, performed on those queries. Right? So think about this problem. Like, the number of queries that people enter is humongous, right? But you can break a query down into particular topics, for instance. So what Google went about doing was understanding how their models were performing across these different query topics. And they came up with this visualization that they called GridViz, I believe, in the paper. And let's talk through this visualization a bit. Across the x-axis, you have topics, right? So these are subpopulations of the data set that they worked on. On the y-axis, you have different versions of models. So for instance, they have variant 1, variant 2, and variant 3 represents 3 different models that they were testing. Now, the width of each of the columns is actually some measure of how large the query topics were. So you can imagine that they might be, the width of each column might be the overall number of queries that fall within these particular topics, right? So the wider a column, perhaps the more queries that are run by users for that particular topic. So we can see that some columns are quite wide, whilst others are much more narrow. And what this would sort of point out to us is if we have if we don't have good model performance on these wider columns, well, that means that we'll really have to sort of drill down and try to understand that, because a lot of users are entering these particular types of queries. But we'll also want to understand, even if our widely utilized query topics are the model is performing well on those, if the model is not performing well on the smaller columns, on the less wide columns, then we'll want to understand those. So we'll be able to set up some mechanism of ensuring that users don't experience negative experiences within those smaller subsets of query topics. Now let's talk also about the sort of colors and the numbers within the boxes. The numbers are sort of numbers between 0 and 1 that represent, well, I'm not sure if they're between 0 and 1, but essentially they're comparisons to some baseline model. So when you see blue, right? Oh, I'm sorry. Let's not talk about colors yet. But when you see negative numbers, it means that this variant is performing less well than some baseline model. Whereas if you see a positive number, this model is performing better than that baseline, right? So they produce this visualization to understand how new models are comparing against their baseline models across these different query topics. And the last thing is that these colors represent the particular metric that they're concerned about. So they are looking at two metrics in this case. The blue represents the AUC, and the red or the orange represents the log loss, right? So they came up with this really cool visualization in order to understand how a model performs, not just in the aggregate, but on individual subslices of data. Now, this is the responsible thing to do, right? You really need to understand how your model is performing on these subslices of your data. This is a much more detailed understanding of model performance instead of just trying to calculate some performance measure like AUC or accuracy or RMSE, right? Because that number in aggregate tells you nothing about individuals, whereas taking a much more nuanced and detailed view will tell you how users will experience the particular models that you're putting out. So in terms of model evaluation, it's very important to do this. The next thing I want to talk about is model deployment, right? And model deployment is a topic that's been getting much more attention in the last several months, in the last, perhaps several years. And it's extremely important because your models cannot begin to deliver any value until they're deployed into an environment where they can be utilized by other users or where they can be utilized by other software systems, right? So the process of getting a model from a training environment to an environment where other people or software systems can use them, I call deploying a model. All right, so the thing I want to talk about here is deployment is an extremely important topic, obviously, and it's extremely important to automate deployment as much as possible. And the reason is you're not going to just deploy one model, right? Because you may have to retrain your model, or you may need to take it offline and switch to another model if you find that it's not performing well on live data. And in order to do that well, your delivery mechanism or your deployment mechanism should be as automated as possible. And there's an idea that's starting to sort of spread throughout machine learning now called continuous delivery for machine learning. And this idea originally comes from traditional software engineering and DevOps, where the point of the process was how can we deploy more changes to our system as seamlessly as possible. And the processes that they came up with are called continuous integration and continuous delivery or continuous deployment. And now people are trying to bring those best practices over to the machine learning development side. So there's a really nice blog post called Continuous Delivery for Machine Learning written by a team at ThoughtWorks that really describes this process. I've also written a number of blog posts on deployment. In fact, I wrote a 10-part series on how to deploy your models, all of the challenges that are involved in this, including, deploying models for batch inference, for online inference, how to A/B test your models, how to iterate on them. And then I concluded with a post on continuous delivery for machine learning. On the right, we have two quotes from another really popular paper in machine learning development called Rules of ML, Best Practices for ML Engineering. And this paper was written by Martin Zinkovich, who is a data scientist / software engineer / researcher at Google. And in this paper, he lays out a number of rules for developing high-quality machine learning systems. And rules 4 and 5 are directly tied to the deployment. And rule number 4 is keep the first model simple and get the infrastructure right. And what he means by this is don't try to add too much complexity into your model before you actually have some system working in production that people are using. The reason for this is there are many reasons for this. One is if your infrastructure doesn't work, it doesn't matter how performant your model is. For instance, if you have data pipelines that aren't producing clean data or aren't working properly, then you're just going to have garbage going into your models, and it won't matter if you have the most performant neural network architecture possible because the data going in is trash. Right. Second, if you develop the infrastructure, if you develop your first model, really, if you develop a first simple model, it's very easy to debug how the system is performing and fix issues if the system is performing badly, right? And then one more reason I'll say is if your infrastructure is there and it's working really well and it's well tested, then you'll be able to iterate on the model much more quickly, right? Because then the process is just about continuing to improve the model performance, and then you can deploy a new model, and then you can collect data and see how that model is performing, iterate, build a new model, deploy that one, right? So spend the time doing the infrastructure right up front, and then you'll be able to much more easily iterate on your models down the road. And speaking of testing, rule number 5 is you want to test the infrastructure that you're using for your machine learning systems independently from the actual model itself. And why this is important is, again, let's go back to that first reason I mentioned. If the data going into your models is trash, well, it doesn't matter how good your model is, because the data is trash, so your model will output nonsensical results. All right, so these 2 rules, which are, sort of really some of the first few rules he spoke about, speak directly to model deployment and its importance. And again, I highly recommend that you read both the blog post Continuous Delivery for ML and Rules of Machine Learning if you're interested in learning about model deployment and delivering machine learning products. And the last thing I want to speak about, and this is really a topic that most people spend no time thinking about, is model monitoring. Now, when you deploy your model, essentially how you've understood its performance thus far is in terms of performance on historical data, right? So even if you have a large amount of historical data, you have no idea how the model is going to perform on live data. You have an estimate of that, but you don't know what's going to happen if the real world changes. And the only thing that you can be certain about is that the real world will change. So if the real world changes, the assumptions upon which your model was originally built may no longer hold. And if that's the case, your model performance, there's a very high chance that your model performance isn't as optimized as you thought it might have been when you calculated it on historical data sets. And the only way to know when things are going wrong is if you're monitoring the models that are deployed. Now, software engineering has a really rich history of monitoring their models. And again, this is sort of a combination of best practices from regular software engineering and also DevOps. Right, there's an entire field called Application Performance Management, or APM, that focuses on monitoring software systems and figuring out if things are going wrong. Now, because machine learning systems are software systems, well, then the tenets of APM hold for machine learning systems. But machine learning systems have their own nuances that require different monitoring solutions than just traditional software. And the reason for this is because your models make assumptions about the real world based on the data sets upon which they were trained. So if your model is not performing well, you need to do things like retrain the model or take the model offline and build some new model to improve on that situation. And again, the only way you know how to do that is if you're monitoring your models. Right? If you're collecting data as it's coming in, you're collecting your model's predictions, and you're seeking to understand, is the model performing as well on this new live data as it performed on the historical data upon which I evaluated the model's performance originally? So this is a really key part of the machine learning product design process, because you need to start thinking about monitoring way before you actually deploy a model. Because if you deploy a model and you have no monitoring in place, well, you have no idea how your model is performing. So if your model is touching end users and they're having negative experiences, well, you'll have no idea, right? You may not have any idea until a really bad thing occurs. For instance, one easy example to understand this is, let's say you trained a lead scoring model, right? This is a very common use case in data science teams. It's a very common marketing problem. And the problem is, well, we have a business generates new leads. We want to understand sort of how likely is this lead to convert so that we can customize the funnel for these new leads, right? We may create some more personalized experience for certain leads over others, given how likely they are to convert. And let's say your model that you've trained to do this lead scoring problem has strong performance in aggregate, but really underperforms on a certain subslice of your data. Let's say leads that are generated from mobile advertisements, right? So if a new lead clicks on a mobile ad and comes to your site or comes to your product, the model performs really badly on those leads. Perhaps it, says they're less likely to convert, even though they're much more likely to convert. If historically you've seen few of these leads, well, then that bad performance will get washed out in the aggregate, right? And if you don't sort of evaluate your model on subslices, as we looked at earlier, then you'll totally miss that. So let's say you haven't done that, right? And now you've deployed your model, and then all of a sudden the marketing team decides to spend a lot more money on mobile ads. And now a larger fraction of our overall pool of leads comes from mobile ads. Well, now our model is performing really poorly on a much larger percentage of our total data, of the total number of leads, and we have no way of knowing this, right? And it may be way too late until we figure out that our model hasn't sort of generated the correct decisions that we would have liked, and now we could have lost out on potentially a lot of revenue, right? So this is just one example where monitoring is important. If instead we had been monitoring our model, well, then we could have caught that situation and dealt with it earlier. And if instead we had also tried to evaluate our model on the historical data by looking at subslices, we may not have even deployed that model to production in the first place, because we would have understood that, hey, if we get more leads that are generated through mobile ads, this model is going to underperform, and that's going to negatively impact our bottom line. So these are the things that I really wanted to focus on today, right? These sort of subparts of the entire machine learning problem. So if you're a data scientist and you've trained your models and you're wondering, well, what happens next? Well, there are many things that happens next. In fact, there are many things that should have happened before, such as the business process of understanding requirements and framing the problem correctly. And then the parts that come after are the model evaluation, the model deployment, and the model monitoring piece. So if you want to read more about these things, I recommend checking out some of the references I have on these slides here. I used many of these references to collect the figures that I use in the slide deck. And there's also a lot of useful information here. Several of these references are actually blog posts on my blog at mlmproduction.com. So I recommend you check those out. And I just want to thank you for giving me your time and listening to this video today. If you're interested in learning more things about production machine learning systems, I highly recommend that you sign up for my newsletter at mlmproduction.com/newsletter. I send out a newsletter every week where I speak specifically about the issues encountered when building production machine learning systems. I also include 5 really curated blog posts, journal articles, podcasts, YouTube videos that I feel educate people on these topics really well. My goal there is to not send people noise, but to really sort of curate the high quality signal that people need in order to learn how to build production ML systems. And if you want to follow me on Twitter or send me a message, you can find me at MLM Production. So thank you very much.